Electric charge is a one-dimensional space. It's a one-dimensional continuous space in classical physics and a one-dimensional discrete space in quantum theory. So these are essentially the things you need to know to get the space of states for one particle. Now, for several particles, it's rather simple and generic. All you do for a two-particle system is you need two three-dimensional positions, and you need two three-dimensional momenta. So you notice for one particle, the space of states is six-dimensional. And so what that means is that for a two-particle state, and we're not including the additional dynamic variable considerations right now. We will get to those later. Those are currently not relevant. The space of states for a single particle is a six-dimensional ordinary flat space. But it's flat space with 6 dimensions rather than flat space with 3 dimensions. Now the way we write this is an ordinary space. We use the capital letter R. We use 2 lines there. This stands for the real numbers. The real numbers is the set of all generic ordinary numbers. 0, the square root of 2, 27, negative 18. It's all possible positive and negative numbers and 0. It's the real numbers. In some sense, it represents a space. It is a space. It's the one-dimensional space which goes on forever in both directions. It's a line. We call R squared a two-dimensional space. We call it R squared because there's an object in set theory called the Cartesian product. It's not very important that we go into the specifics on it, but R squared is the two-dimensional space. R squared is just a pair of real numbers, an ordered pair of real numbers. So you would have, say, 6 and minus pi over the square root of 18. That would be an element of R squared. Now, this element is not the same as minus pi over the square root of 18, 6. So, the important thing to remember, once you add additional dimensions to this, is that the order is very important. The order matters. These are 2 different points. Now, in general, if you want a space which is a flat space that goes on forever in every direction, an ordinary flat space with a nice trivial topological structure, then if you want an n-dimensional space, it's just R to the n. And what is R to the n? R to the n is a set of n ordered objects, and they form an ordered pair. Every single one, or not an ordered pair, an ordered n tuplet. Every single element is a real number. Every single element can be any number from the real numbers. It could be 0, it could be 28, it could be negative 5, whatever. And so that's in general what an n-dimensional space is, the simplest n-dimensional space. So, if we have one particle, we have a 6-dimensional space. If we have 2 particles, we have 2 3-dimensional positions, 2 3-dimensional momenta, and as far as the space of states is concerned, all of those are independent. They're not independent typically when it comes to the law of evolution, how fast one particle is moving, where one particle is located and how fast it's moving is relevant to where one other particle is located and how fast that other particle is moving. But that's taken into account in the laws of evolution. For the space of states, they're independent. And what that means is you could start, if you have two particles, you could put them anywhere with respect to each other. They could be located anywhere, and they could be moving in any direction, at any speed. And the law of evolution of the system is what causes them to be entangled with each other. So, for two states, we have two of these. For two particle states, we have two of these and two of these. That gives us a 12-dimensional space. And so, in general, the space of states for n particles is r to the 6n. In Newtonian physics, this is called phase space. There's another space, which is just the set of positions, and for certain kinds of interactions, that can be sufficient. That space is r to the 3n, and that is called configuration space. Now note, we're not taking into account things like electric charge and other potential variables. There are two reasons we're not taking them into account. One, for the simplest physical laws, you don't need them. And two, they often obey certain conservation principles, which means you can simply fix them as a certain number, and that number really doesn't change all that much. Sometimes it can change if we have more complicated setups you can imagine, but that's neither here nor there. That's not important for this particular example. For the most simple Newtonian physical theories, it consists of one particle states or n particle states, and the dimension for an n particle state is 6 times n, where n is the number of particles. And that is the generic space of states for Newtonian physics. Now, Newtonian physics has to tell you something else. That additional thing that it needs to tell you is, how do the spaces evolve over time? That is a more complicated principle. That's a more complicated idea. And in general, it requires calculus. So, on these videos, I will be assuming that you are familiar with calculus. If you're not familiar with calculus, then these videos will be difficult for you to follow. The law of evolution for a system is that, this is Newton's second law. Newton's first law, Newton's laws of motion. The first law of motion is that an object, a particle, which is not being interacted with at all, travels in a straight line at a constant velocity. Straight line at a constant velocity. That is to say, if your velocity vector is not changing at all, if your momentum is not being altered, then you're just going to forever travel in the same direction at the same speed. So you're just going to move in a line. That is to say that for particles that are not being interacted with, the position x as a function of time, this is your position along the x-axis, is just equal to your velocity along the x-axis times time, times the point in time that you're at, plus x0. x0 is the position in the x direction that you were at when t equals 0. And in general, for a particle in 3 dimensions, you have to include these 3 possibilities.